Find the radius of convergence of the series, and within this radius, the sum of the series as a function of x. Okay, we are given the series, or the sum, from n equals 0 to infinity of x squared plus 1 to the all that to the nth power over 4 to the n plus 1. So before we start evaluating this, it'll be helpful if we just do some algebraic simplification. So this is going to be equal to the sum from n equals 0 to infinity. We can just keep this the same, x squared plus 1, all that to the nth power. And now down here in the denominator we can separate the 4 to the n and the 4 to the 1 power, and that just gives us 4 to the nth power times 4. And then we can pull out a 1 over 4 here, and we can put everything that is to the nth power under the same in the same brackets. So this is going to equal our sum from n equals 0 to infinity of 1 over 4. And then we just have an x squared plus 1 over 4. All of that to the nth power. So what we have here now is a geometric series. This 1 over 4 here is what we would consider our a term. And then the x squared plus 1 over 4, this is just going to be our common ratio. And because we are starting at n equals 0 down here, we only need our common ratio to be raised to the nth power. If, however, n were starting at 1, we would need this to be an n minus 1. So this is a little bit lucky here that we just happen to get a problem that asks us to start at 0, and it works out that we have to the nth power, and we don't have to do any further algebraic manipulation like we might see in some other problems. So we know from a geometric series that this sum along its interval of convergence is just going to be equal to, this is just going to be equal to our a value, which is 1 over 4, divided by 1 minus our common ratio. Well, our common ratio is all of this business, x squared plus 1 over 4. And if we just multiply our numerator and our denominator here by 4, we get a 1 over 4 minus x squared minus 1. The 4 here and the 4 in the above it would cancel out, and we would just have a 4 here. And 4 minus x squared minus 1 is just going to equal 3 minus x squared. And this is going to be the sum of the series. So this right here is the sum of our series. But we still need to figure out what the radius of convergence is going to come out to. And it's good that we have simplified things here to this geometric form here, because when we do our ratio test, it just makes it easier to take our n plus 1 to figure out what our n plus 1th power is going to be. So that way we don't have a bunch of n plus 1s and n plus 1s up here that we're trying to evaluate for. So let me just section this off here. And we're going to do our ratio test. Just to figure out what our interval of convergence is going to be. We're going to take the limit as n approaches infinity of the absolute value of this to the n plus 1th power. So we have 1 over 4 times x squared plus 1 over 4 to the n plus 1 power. All of that over 1 over 4 to the x squared plus 1 over 4 the nth power. Alright, so you can see that here we're going to have a 1 over 4 and a 1 over 4 that cancel out in the numerator and the denominator. Here we're going to have x squared plus 1 over 4 to the nth power, which is going to cancel out with our x squared plus 1 over 4 to the nth power down here. And what we're going to be left with, so it was an absolute value term, what we're going to be left with, this is just going to go to this to the 1th power over here. This is just going to go to x squared plus 1 over 4, which is what we had left over up here when we had our x squared plus 1 over 4. The nth term canceled out with what was down here, and we were just left with all of this to the 1 power, which is what we have here. So if we say that we know that to find our interval of convergence, this must be less than 1. So x squared plus 1 over 4. In order for this to converge, this must be less than 1. So when we multiply 1 by 4, or multiply both sides by 4, then we stick our 4 over here. Then we're going to subtract this 1 right here from both sides, and that's going to get us to x squared is less than 3. And if we take the square root of both sides, that is just going to get us to x is less than positive or negative square root of 3, which means that our radius of convergence, we'll just call it r here, our radius of convergence is going to equal root 3. Now, because this is a purely geometric series, there is no need to test the endpoints. So we know that if we have endpoints of positive or negative root 3, well then this is just going to become a divergent series here. If, however, we had some other, x and n terms outside of here, well then we might want to be more careful to evaluate our endpoints here. But because we know that this is a purely geometric series, that we've been able to algebraic manipulate this and simplify it down to where we just have our a term here and our common ratio to the nth power here, we know that if x were to equal positive or negative root 3, then this series would diverge. It's only going to converge in between our interval of x equals negative root 3 and x equals positive root 3. So then we're done. This is going to give us our interval of convergence here and our radius of convergence there.